Southeastern University.
We're from traditional programming. In traditional programming, we have our computer. We typically feed in both data and a program, and then we expect some sort of output. So an example of this is, suppose we have a list of strings, and we have a function that finds the string length for each of those strings. Then as they're fed into the computer, our output would be a list of all the lengths of all the strings. So that's just like one example of a function, but we can imagine like we have data and then we know what we want to do with it, and we like run that program on that data. In machine learning, on the other hand, what we have is we have data and corresponding output or labels. Typically, this is in supervised machine learning. I'll briefly touch on the difference between supervised and unsupervised machine learning. But we have the data and its output, and we're trying to find a program which correctly predicts the relationship between the data and its output. So, for example, if we think of that same example of a list of strings and string lengths, then our data in that case could be the list of strings, and our output could be the corresponding string lengths. And we're trying to come up with a program that, like, given in any new string or list of strings, can predict their outputs based on the patterns that it's noticed between the original given data and outputs, which are typically called labels. So like this ranges across a whole variety of examples, and we'll discuss some other ones that we've seen in a little bit. But as I've mentioned, one thing that we want to pay attention to or want to look at is supervised versus unsupervised machine learning. So supervised machine learning algorithms use labeled data to train the model and make predictions. So this is the case where we have the data that we're fed in, and we also have their corresponding labels. So for example, we have a data set with a series of vectors x values, and then their labels y values. And we're trying to find a model that takes in any x and outputs a corresponding y. So that's probably a pattern that you've seen before or will see in the future if you continue down the line of machine learning. On the other hand, unsupervised machine learning algorithms are used when the training data has not yet been classified or labeled. So this is when the machine tries to find interesting patterns in the data. One kind of fun application that I like thinking about here is for supervised machine learning versus unsupervised. Imagine that you have a kid and you also have a pet dog. Your kid kind of learns, oh, like, this is my pet dog. You aren't like showing the kid, here is a picture of a dog, and this is, I mean, you might be, but let's suppose we aren't showing our kid a picture of a bunch of dogs and saying, this is a dog, this is a dog, this is a dog, showing them a picture of like a cat saying, this is not a dog, this is not a dog. But yet when they see our dog and they go outside and then they see other dogs, they might still know, oh, dog. So they're just finding patterns and they're learning, oh, like this has 2 ears and doesn't have whiskers and has like a tail and is furry. This is a dog. So that's kind of like how I like to think about unsupervised machine learning. And then within supervised machine learning, there's kind of 2 main categories. There's classification and regression. So classification is a form of machine learning, form of supervised machine learning that goes from a data space to a discrete space of predictions. So what this means is, suppose we have a few different like possible categories, then these are all of our labels. So a common example of this is like labeling mail as spam or not spam. So we see that there's 2 output classes. There's a discrete space of predictions, either spam or not spam, and we're predicting which category our like input belongs in, as opposed to regression, which is a form of machine learning that goes from a data space to a continuous space of predictions, where our model is some continuous function. So for example, we can't bin like housing prices into like, oh, this is, I mean, we theoretically could like bin it into like $10,000 ranges or whatever, but let's say we're thinking about all possible prices. This is an infinite scale, so practically infinite scale. So this has a continuous space of predictions. It's not like, oh, it's either like 50 or like $75,032.06. Like there's a lot of different output bins, so it's not discrete, but instead continuous. So with all of that being said, as we're kind of approaching the content today, and as you're kind of absorbing and learning about machine learning across the board, some of the key issues and the questions to always keep in the back of your mind are, what are good models to use? So models, this like falls into like, should we use regression or a specific classification model? Some examples of those are like logistic regression or support vector machines or like random forests. No worries if these are unfamiliar to you now. We're not going to be worrying about the specific models in this course, but that is an important question. Okay, what model do we even use for this problem, and how do we go about finding that best model? Beyond that, like how can we optimize for the accuracy of unseen data? So in that first diagram, we saw that we're feeding in data and outputs to train our model, or even if we're just feeding in data, we always have like some initial set, and then we either try to find patterns or a model that will be able to predict it moving forward. So what do we mean by moving forward? When we see new data, are we able to predict it properly? How much data do we need to be confident in our results? This is just this is a huge question across the board right now. Like as we're dealing with big data, and as it's even a stats question as well, like how many subjects do we need in a sample to be confident in our results? And then beyond that, like do we have enough data where this will generalize to unseen data? And then last but not least, when we're like entering in this data, how can we even deal with challenging data? Sometimes it'll have missing data points or errors or outliers. Sometimes it'll be really high dimensional and it's hard to deal with. Or on that same train, like really large data sets, and it's just inefficient to feed it into some model. So these are just like questions that we won't really dive into today, but that are good to keep in the back of your mind when thinking about machine learning moving forward. So with all that being said, before we move on, I want to open this up to you guys, and I want us to just like talk about, okay, what do you think what are some examples of where you've seen machine learning in everyday life? Hint, it's kind of everywhere, but it'd be fun to like have a discussion about what we've seen working with. So I'll give you guys a couple of minutes to just share some of your thoughts there. Appreciate that. This is all key. So I'll be switching back and forth. I have a little like whiteboard app. Hopefully you guys can all see this okay. But so some examples of what this like recipe looks like. So for an example data set or task could be like predicting housing prices. The relevant features here are the things that we want to look at in each of the houses, like number of bedrooms, number of bathrooms, or square footage. An example of a model, typically for predicting housing prices, we use linear regression, where we just do a linear combination of all the different features and come up with like an equation where we pass in all these features and predict a like singular output, which is price. For this example, I've used mean squared error before, where you're just finding the like mean squared error between your predicted values and the actual values. And then optimizers are both gradient descent and closed form solution. If any of this feels like is confusing, we can take a closer look at each of these parts, but essentially just this is like the big picture, and I'm trying to show you like in this step, this is where it's integral to no calculus, and you can't remove any of these steps in kind of general machine learning. I see ID is saying, I didn't pass calculus at school. No worries at all. It's a tough concept. We're going to try to break down some of the parts and hopefully make it a little more digestible. And then this presentation and these slides will be available later, so you can I write out some of the typical rules for taking derivatives and some of the different tools you can use. So no worries at all. We'll get through the material together. So that's blocking that. Okay, so another example of kind of a data set or task. It could be, for example, let's kind of like we were talking about before, we have a bunch of images of dogs and cats, and we want to classify them as either dogs or cats. Some of the features here might be like the size of the animal. FF is pointing out what I said, integral to no calculus. Awesome. That's a good pun. Perfect. So features could be size, like the head shape of whatever we're looking at. Like if it's has a long pointed, I guess that could be a dog. If it has like a if its head shape is like square, that's probably not a dog. So image features could be another example, like I've mentioned before, like tail or ears, furry, like pixel location, pixel distribution. These could all be features that we pull out of these images. Models that we could use anything that does classification, so neural network or logistic regression. Optimizer, MSE is often used. I'll keep that there. Like MSE, just any accuracy metric. And then for this optimizer, I'd probably use gradient descent, and we'll talk more about gradient descent moving forward. So this is just an example of like, okay, we have our data set, we have our features that we're going to plot from the data set, we know what we're going to use, how we're going to evaluate what we're going to use, and then how to actually get the best values for our model. So this is kind of a general story that you'll see time and time again, and we're going to focus on this optimizer step today. So with that being said, in order to, like one of the big things that is relevant is derivatives, and working up to differentiation. There's kind of a few things that we can start with to build contexts. So first I'm going to walk us through like looking at functions and graphs, and then we're going to work up to limits. And then from there we can kind of talk about briefly the definition of a derivative, but more so the applications and like actually taking derivatives. So what is a function? I'm sure you've heard of a function before. It's essentially a relation between a set of inputs A and a set of outputs B, such that each element in A is mapped to a single value in B. So, for example, if we, like, these are two examples of functions where we're given our inputs X, and then they have a single output Y. So like a way to check this is the vertical line test. You draw a vertical line at any point in the graph. If it only hits one value, then it's a function. If it hits like two values, then it's not technically a function. So for example, like parabolas, e to the x, these are both functions. But non-functions are like, this is the equation of a circle, or no, this is the equation of a circle. This guy's graphed over here. It's just like a sideways parabola. We can see that there's two values of x, or there's this one value of x mapped to two different values of y, which means it doesn't classify as a function. So we can still take derivatives of non-functions. Just the technical formal definition of a derivative is defined over functions, and like we can find limits of functions. So it's always important to have like the general definitions in the backing to support some of those future concepts. So like a function is useful, but even more important, we can like graphically represent functions, which help us with coordinate geometry, which allow us to like visualize what's going on a little bit more. So ID is asking, why is it important to know what is a function and what not, in the sense of input and output? Yeah, kind of like what I was just saying, like a lot of different rules and a lot of different theorems are built off of assumptions that we're dealing with functions. And that's what functions are defined as. To use math formulas, or like more so to use theorems. We'll see examples of like when we take a look at like partial derivatives, some of those might not be functions. They are with respect to each variable, but they're not kind of overall. So it's just like what a lot of future definitions are based off of, and an important context to have. But if you don't like memorize specifically what a function looks like, you shouldn't get too tripped up on later concepts. Hopefully. So we can graphically represent functions with coordinate geometry. So like if f of x is a function, then the graph is essentially like drawing all the points of x in like a certain plane, and where like the function maps that point. And then graphs do not need to be functions of the form points x, y satisfying any relation. So as long as we have x and y, we can create a graph. And then we can also like, instead of like once we draw all the points, if there's like a trend, we can like connect the points, and that gives us like a line of a function. So with graphs, that we're going to switch over to Jupyter notebooks for the first exercises. So, oops, looks like, let's hope, I might need to run this again. Okay, let me just open this up again. So you guys should have the link to the Katacoda, and then you should be able to open up the Jupyter notebook for this course. I just had it open for too long, so it might be. Sorry about this. Let me just move this off to the side while I get this up and running. If not, I'll just run it locally, but so I have some questions that I can ask while this just boots up. So the first one by AS is asking, I was just wondering, and then links to this link, which I will check out later. We need to use Python libraries in order to call these math functions, but conceptually, theoretically, we must be aware of what's happening under the hood, correct? I'm not sure what the link is, but we are, like, through the notebooks today, we are using math functions, and like a lot of the like scikit-learn, which is what you might use to do a lot of machine learning, there are like built-in functions where you don't really need to know anything about calculus, but I think like you'll oftentimes have to tweak models and make different assumptions about efficiency and stuff, where if you don't know what's happening under the hood, you could get caught on like some issue that you're not aware of, or it will just like limit your like ability and range of knowledge. So I think for that reason, it's really important to have an understanding of what's happening under the hood. And then are functions defined for each, as for each x, you only get one solution for f of x for y? Yep, each x can only have one corresponding solution. And someone's saying it takes a second to boot up. Yep, I booted them up earlier. I think it's just, computer might be being slow. I think we're all set. Let me just zoom that in a little bit. Okay, so hopefully you guys can see this. So first, there were some issues with the Katacoda scenario, like with the SymPy dependency. So I'm just importing it inline, which is not always best practice, but that's what we are working with today. And then just make sure you run your imports before we get to the different notebooks. Otherwise, it will not work as expected. So matplotlib is a Python visualization library built on top of NumPy. So it allows you to generate plots, histograms, bar charts, many other types of graph. Seaborn's another visualization library, which kind of works closely with matplotlib. So having like an understanding of like how to deal with matplotlib allows you to make a bunch of visualizations and work with other like libraries and extensions that work on top of it. So super helpful. Just being able to visualize data is kind of essential at many stages of the data cleaning, analysis, manipulation, and then model evaluation steps. So, or even figuring out which features might be relevant, or like so many different tasks along the process of actually using machine learning. So first thing we're going to do, first thing I'm going to show is like I created just a grid where we like from -4 to 4 up to 16, where we're defining our function y equals x squared, and we're just saying that it shows a parabola. So I'm just plotting. First I define all of the x values, which is all values spaced out by 4. All values between 100 different values between -4 and 4, and then I define our function as like all those values squared, and then I just plot all these values, and the R indicates red, and then I just show the plot. So this is kind of like basic graphing a function, basic plot, and then I wanted to like visualize a few of the important functions or graphs to be able to recognize that kind of come up and are essential for when we're learning different rules and are just most common functions that come up. So ignore all of the like fluff here. This is just for formatting. If you're curious, you can look at what I did. There might be other efficient ways to do it too, but essentially I got a line space between -10 and 10, also, once again 100 points. And I'm plotting like x squared, x cubed, e to the x, log of x, and 1. So here we can see all the different plots. So this is y equals x squared. Here we can see y equals x cubed, log of x, where kind of know that the log of negative number isn't defined. Y equals x is just a line. E to the x gives us this shape, and then a constant is always just like y equals a constant is always just a horizontal line. So these are good functions to know, and it's also useful to be able to plot. So with that being said, we have two other functions where just like no need to go too fancy, but just plot the following functions. I'll give you guys like a few minutes, like maybe 5 minutes, to just go through and make each of these plots. I'm going to send out a pulse check. And then, so just hit the green thumbs up when you're like, once you've answered, if it makes sense, if you're all set, and then red thumbs down if you're completely lost and don't know where to go next. So, I'll give you guys like about 4 more minutes to work on that, and then we'll regroup and go over it together. Function, we're going to do the same thing. We just plot the x, y. I'll make this one blue. I think by default it's blue if I don't specify that. And then I'm just going to show the plot. So here we see our e to the 2x minus 2x. You can see it kind of approaches a large value really fast. So I'm seeing FF also said that just defining y equals, it looks like np.x. Ooh, yeah. Okay. Yeah, using NumPy is probably reliable to just using math. So yeah, that's awesome. That's a really good point. I'm not going to implement that right now, just for the matter of time, but thanks, FF. So we're going to switch gears back to our slides. Let me just end that pulse check. Send out a quick poll.